The next presentation is entitled Oxygen Insertion Mechanisms in Selective and Complete Oxidation of C4 Hydrocarbons. Umit Ozkan, M.R. Brown, and S.A. Sinha and T.K. Pincarinia from Ohio State University. Umit Ozkan will make the presentation.
Thank you, Jim. Can I have the first slide, please? I will be talking about oxygen insertion and selective and complete oxidation of C4 hydrocarbons. And in doing this, I will be referring to the results of studies carried out by my graduate students, Marianne Brown, Sharon Sanger, and Todd Pancarina. Although her name is not included on this slide, I will also be referring to some work carried out by my research associate, Li-Ping Chang. The catalytic system we have focused on is molybdenum trioxide. Our earlier studies on molybdenum trioxide have indicated that molybdenum trioxide is capable of catalyzing the formation reaction of maleic anhydride from C4 hydrocarbons, but it is not a very selective catalyst. When we try to change the catalytic behavior of molybdenum trioxide by incorporating some simple molybdates into it, we saw that incorporation of manganese molybdate had a very strong promoter effect over molybdenum trioxide's catalytic behavior. So in this talk, I will be concentrating on these three sets of catalysts: pure molybdenum trioxide, the promoter in pure form manganese molybdate, and finally the promoter catalyst. Although we have looked at a large range of concentrations for the promoter, I will be talking about a specific promoter level, which is manganese molybdate to molybdenum trioxide level being equal to 0.15. I'd like to give a brief overview of the type of experiments we have performed over these catalytic systems. We have done fairly extensive characterization work, which included BET surface area measurements, pore-size distribution, X-ray diffraction, laser Raman spectroscopy, and Raman microprobe, scanning electron microscopy, which was combined with energy dispersive X-ray analysis, and finally X-ray electron spectroscopy. I will not have time to go through all the results. I will briefly mention some of the XPS results we have obtained. But the characterization work showed that there are two distinct phases existing in these promoted catalysts. In other words, molybdenum trioxide and manganese molybdate coexist as distinct separate phases in the promoted catalyst. But the most important feature that we observe is the close intimate contact between the two phases. None of the characterization work indicated the formation of a new compound, a new phase, or a solid solution. We have done steady-state reaction experiments using a continuous integral fixed-bed reactor. The purpose was to assess the effect of oxygen concentration. In doing this, first we started off with butene as the feed material. Butene is the reactant in this case. And then we repeated the same experiments using what we believe are the intermediates in the reaction network from 1-butene to maleic anhydride, 1,3-butadiene, and furan. Finally, we used the product itself, which is maleic anhydride, as the feed material in the reactor. We have also done some pulse reaction experiments. In the first phase of our studies, we used pulses which contained no oxygen. In other words, we pulsed the catalyst bed using feed mixtures which contained only nitrogen and hydrocarbon. In the second phase of our studies, we pulsed the catalyst beds using feed mixtures which contained isotopically labeled oxygen. In other words, the mixtures consisted of oxygen 18, hydrocarbon, and nitrogen. I will be talking about some of the isotopically labeled oxygen study results shortly. And finally, we have done some high-temperature oxygen resorption experiments to compare the oxygen uptake capability of these different catalysts on both fresh catalysts as well as reduced catalysts. Now, I'll go over some of the results very quickly. Here we are looking at, I don't think it's very well focused. We're looking at pure molybdenum trioxide here, and the hydrocarbon feed is butane. We see that the increasing oxygen concentration seems to encourage complete oxidation more than selective oxidation products. Here we see butadiene, which is in top curve in pink.
The other one.
The curve in pink is decreasing with increasing oxygen concentration. Carbon dioxide is increasing. There's a very slight increase in maleic anhydride also, but the selectivity of maleic anhydride is rather low. When we switch to 1,3-butadiene as the feed material, we see maleic anhydride selectivity going through some sort of a broad maximum. The selectivity to carbon dioxide increasing, and small quantities of furan and chlorine also being formed. Finally, when we come to furan oxidation, again concentrating on the molybdenum trioxide catalyst, we see that the selectivity to maleic anhydride decreases much more pronouncedly, and the selectivity to carbon dioxide increases almost as rapidly as maleic anhydride selectivity decreases. And we see very small quantities of acrolein being formed, and there's almost no other reaction products. Now, the picture somewhat changes when we look at the promoter itself, pure manganese molybdate. The adverse effect of oxygen concentration on selective oxidation products is much more noticeable in this case. Here, starting out with butene as the feed material, the selectivity to butadiene is increasing with increasing oxygen concentration, and selectivity to carbon dioxide decreasing. And there is no maleic anhydride detected in the oxygen concentration range that we looked at. When we use 1,3-butadiene, which is the reaction intermediate as feed material, the selectivity to carbon dioxide gets very, very high. It becomes the dominating reaction product. Another interesting feature that we see here is the selectivity to furan increasing very rapidly with increasing oxygen concentration, suggesting possibly two things. One is that formation of furan over manganese molybdate does not require presence of gas-phase oxygen. It is more associated with the lattice oxygen. And it could also suggest a possible competition between butadiene and oxygen for the same catalytic site. When we use furan oxidation over manganese molybdate, the only oxidation products that we observe are complete oxidation products. Now, the behavior is quite different over the promoted catalyst. First of all, we see that there is some increase over the maleic anhydride formation with increasing oxygen concentration. We see that at oxygen deficient region, which is oxygen levels below 11%, carbon dioxide is the major reaction product. However, at higher oxygen concentrations, maleic anhydride becomes the major reaction product and appears to increase with increasing oxygen concentration. And we see that selectivity to butadiene decreasing as it did on every catalyst with increasing oxygen concentration. Now, when we use 1,3-butadiene as the feed material, one of the important things we observe is that selectivity to maleic anhydride gets fairly high, and it is the major reaction product throughout the oxygen concentration range that we looked at. At rather high oxygen concentrations, the carbon dioxide catches up with it and gets increasing, and one can probably safely speculate that if we increase the oxygen concentration further, carbon dioxide would become the major reaction product. When we use furan as peak material, the selectivity to maleic anhydride gets around 70% range, and the selectivity to carbon dioxide shows almost a mirror image of selectivity to maleic anhydride. Now, we also use, as I mentioned earlier, the product itself as the peak material to see what type of electrolyte oxidation behavior we would observe. We immediately saw that the catalyst, which seemed to have the highest activity for maleic anhydride complete oxidation, was manganese molybdate, and the lowest one was the promoted catalyst, the one at the bottom. We have also seen that the carbon dioxide yield over the promoter itself, manganese molybdate, didn't seem to be very sensitive to oxygen concentration. The carbon dioxide yields over the promoted catalyst and the molybdenum trioxide showed some increase with increasing oxygen concentration. Now I will move on to oxygen 18 pulse experiments and mention a few of the results. Again, we are looking at pure molybdenum trioxide catalyst here, and each of the bars represent a different carbon dioxide isotope. Except for the first pulse, we see that the largest percentage of carbon dioxide isotope has a molecular weight of 46. In other words, it contains one oxygen 16 atom and one oxygen 18 atom. The second largest percentage is occupied by carbon dioxide, which has only oxygen 16 atoms, and the smallest, the shortest bars that you see here are the ones which contain two oxygen 18 atoms. The behavior remains the same over the manganese molybdate catalyst, although the isotopes for carbon dioxides with molecular weights 44 and 46 are somewhat closer together. When we move to the promoted catalyst, the picture changes quite a bit. First of all, we see that the largest percentage of carbon dioxide isotope is the one which contains only oxygen 16 atoms in it, and it shows that the largest percentage of carbon dioxide has something to do with the lattice oxygen rather than gas phase oxygen. And if we make an overall calculation, we see that about 75% of all oxygen incorporated into carbon dioxide molecules are oxygen 16, meaning they have been extracted from the lattice structure of the catalyst. Now we have made similar comparisons for furan isotopes. This is pure molybdenum trioxide, and we see that about 85% of oxygen in furan isotopes comes from the lattice oxygen, being oxygen 16. The percentages are closer together, or pure manganese molybdate. The percentages are about 65% or about, in some cases, 60% for oxygen 16 and about 40% for oxygen 18. That means for manganese molybdate, the lattice oxygen does play an important role, but we also start seeing incorporation of gas phase oxygen into the hydrocarbon molecule. Over the promoted catalyst, however, we see that more than 90% of the oxygen in furan isotopes is oxygen 16, which again is associated with the lattice oxygen. Now, maleic anhydride was observed only over the promoted catalyst in these pulse reaction experiments, and again we compared the isotope distribution. The largest percentage is occupied by maleic anhydride isotopes, which contain two oxygen 16 atoms and one oxygen 18 atoms with molecular weight of 100. The second largest one is molecular weight 98, which is three oxygen 16 atoms. And the smallest one is the one with 2 oxygen 18 atoms and 1 oxygen 16 atoms. And we haven't observed any molecular hydride isotopes which contain 3 oxygen 18 atoms. And again, if we make a rough calculation, we see that about 75% of all oxygen that we saw in the molecular hydride is oxygen 16, which is associated with lattice. I won't have time to go through all of them, but we have made similar observations over other reaction products like water or acrolein, and over the impregnated catalyst, we have seen that the majority of the oxygen which has been incorporated into these oxidation products has come from the lattice of the catalyst. Now, the results so far are indicating that there is a redox mechanism which is taking place over the catalyst for incorporation of oxygen into the hydrocarbon molecule, and this seems to be true for both complete oxidation and selective oxidation products. One other interesting result that I'd like to quickly mention is oxygen chemisorption results that we have performed at 400 degrees centigrade. We compared the oxygen uptake of these 3 catalysts, and we have seen that the highest oxygen uptake is observed over the promoted catalyst, followed by the promoter itself, manganese molybdate, and finally molybdenum trioxide. When we have done similar chemisorption experiments over the reduced samples, we have seen that the highest degree of reduction was observed over the promoted catalyst. Next one was molybdenum trioxide, and it was followed by manganese molybdate. So we have seen that the promoted catalyst seems to be reduced more easily, and it also has the highest oxygen uptake. Now finally, this set of results is really very, very recent. It's so recent that we don't have a chance to repeat or reproduce the results, but I'll mention them very cautiously. When we have done XPS studies over these catalysts, we have seen that the promoted catalyst, which was reduced, showed some binding energy shifts. There was a positive binding energy shifts for manganese 2p 3/2 binding energy, and a negative binding energy shifts for molybdenum 3d 5/2 binding energy. And we have a feeling that this may give us some clues about why the promoted catalyst is behaving the way it is. And we are suspecting that it may have something to do with the electron exchange between the cations, manganese and molybdenum, over the promoted catalyst. Finally, I'd like to acknowledge the financial support provided for this work, which was initiated by Ohio State University Office of Research and Graduate Studies, which was followed by grants from the California Technologies Laboratories through the Department of Energy, MX Foundation, and Petroleum Research Fund. Thank you.
We have time for maybe one question.
Have you done any calculations about the amount of product that you've made in comparison to what would be a monolayer coverage of oxygen over your catalyst to know if you are removing essentially a monolayer of oxygen and reducing to the fourth state?
Well, the catalysts we have used were degassed under vacuum at high temperatures, so we don't believe that there is any chemical
right.
oxygen left over on the catalyst. And we have continued some of the pulses. I have only shown 5 pulses, but we have continued. And the trend seems to continue. Towards the end, we started seeing more oxygenating, indicating that the lattice oxygen is being replenished by the gas phase oxygen. But I don't believe it's just the chemisorption or monolayer oxygen on the surface, which is being incorporated into the hydrocarbon.
One last question by Halcom.
In the data that you showed, we don't believe you tell us the conversion. Can you tell us how does the oxygen isotope distribution as well as the selectivity change in the conversion?
Well, I guess I was expecting that question. Although I haven't shown here, we have done a large number of experiments looking at these catalysts at equal conversion levels. So the promoter effect that we observe is real. And we have seen that when we keep the conversion constant, the highest selectivity to moleic anhydride is observed over the promoted catalyst. And those results will appear in Journal of Catalysis in a table which has been accepted recently. But coming back to your question, the conversion levels for the results that I have shown vary about from 40 to 60%. So they are not low conversion, medium conversion levels.
We're getting behind now. Thank you very much. So please.